Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951A6602. I'm studying in CSC AI and ML, that is Computer Science and Engineering, with a specialization of Artificial Intelligence and Machine Learning, fourth semester, Institute of Aeronautical Engineering. In this tech talk video of the subject of design and analysis of algorithms, that is DAA, the topic I am going to speak upon is a semantic graph of traffic scenes for intelligent vehicle systems. Now let's go through the contents. In the first place, I'm going to explain about the introduction. I'm going to introduce the topic of semantic traffic scene graphs. There will be understanding structured scene representation, and after that I'm going to explain about the need for semantic representation in traffic analysis. There will be discussing about why raw sensor data is not enough, and after that we'll go through graph based modeling of traffic scenes. There will be discussing about nodes, edges and relationships, and after that we're going to be discussing about algorithmic construction of semantic graphs, building semantic graphs from sensor data. After that, I'll be speaking upon applications in intelligent vehicle systems, the real world use cases and challenges. And after that, I'll, I'll be explaining about real-time performance requirements. There we'll be discussing about significance of real-time reasoning. And after that, algorithmic challenges and optimization techniques. We'll be discussing about potential challenges and applicable strategies. And finally, after that, I'm going to conclude the topic with an overall summary. Now, let's go through the introduction to semantic traffic scene graphs. Intelligent vehicle systems demand precise comprehension of intricate traffic environments to operate safely and efficiently. Traditional sensor technologies, including cameras, LiDAR, radar, generate vast quantities of raw data but lack the structured interpretation necessary for high-level decision making. Semantic graphs bridge this gap by providing a structured, meaningful representation of the traffic scenes from the raw data. It does it by modeling traffic elements as interconnected graph structures. We can leverage algorithmic techniques from design and analysis of algorithms to enable intelligent reasoning, optimal path planning, and robust collision avoidance. Hence, that was all about the introduction. Now let's discuss about the need for semantic representation in traffic analysis. First of all, dynamic complexity. Traffic environments are highly dynamic with constantly changing conditions. Raw sensor data alone can't capture the nuanced relationships with and hierarchical structures essential for safe navigation. High-level reasoning. Vehicles must understand object types, those are cars, pedestrians, and signals, spatial relationships like distance, direction, and logical priorities, right of way rules to make informed decisions. Knowledge conversion. Semantic representation transforms low-level sensor data into high-level knowledge, enabling algorithms to reason logically rather than react blindly to stimuli. Hence, that was all about the need for it. And now let's discuss about graph-based modeling of traffic scenes. The traffic scenes exhibit natural graph-like properties, making graph theory an ideal framework for representation and analysis. This structured approach enables efficient computational reasoning using established algorithmic principles. The graph nodes represent vehicles. Vehicles include cars, lorries, motorcycles, or whatever we know. Pedestrians and cyclists, road infrastructure elements, traffic signs and signals, and lane boundaries and markers. Graph edges represent spatial relations such as near, far, ahead, behind, motion relations, approaching, overtaking, following, come under them, and logical relations, right of way, priority, and finally temporal dependencies. This graph structure enables efficient traversal and analysis using fundamental DAA principles using BFS, DFS, and shortest path algorithms. Hence, that was all about graph-based modeling of traffic scenes. Now let's go through the algorithmic construction of semantic graphs. First of all, raw sensor data is taken and object detection is done. From the data, objects are detected, and after that, the objects are created as nodes, and after that, relationship inference. The relationships are established. The construction pipeline begins with raw sensor fusion, where perception algorithms detect and classify objects. These entities become graph nodes, whilst spatial and temporal algorithms infer relationships to form edges. Dynamic updating Dynamic updating ensures the graph remains current as the new traffic scene evolves. The graph traversal, BFS and DFS for scene exploration can be implemented, and after that the shortest path. For the shortest path, Dijkstra's and A pointer algorithms for route planning can be implemented, and constraint optimization. For that, satisfying multiple objectives simultaneously can be done. Hence, that was all about algorithmic construction for semantic graphs. Now let's discuss about applications in intelligent vehicle systems. Semantic traffic scenes are represented as graphs, and those graphs enable a wide range of critical applications in autonomous driving systems. Those applications, four of them are path planning, that is utilizing shortest path algorithms to compute optimal routes whilst respecting traffic rules and minimizing travel time. Collision avoidance, that is analyzing spatial relationships to predict potential conflicts and execute evasive maneuvers. And intersection navigation, that is reasoning about priority rules and right of way to make safe decisions at complex junctions. And after that, lane management, that is evaluating lane changing and overtaking opportunities based on neighboring vehicle trajectories. And that was all about the applications. Now let's discuss about the real-time performance requirements. Here we have three requirements: 100 milliseconds of decision latency, maximum acceptable delay for critical safety decisions in autonomous systems. Decision latency is applied over there, and after 10 Hz of update frequency. It is the minimum rate for graph reconstruction to maintain scene accuracy. And 1000 plus graph nodes. Graph nodes, more than 1000 of them. It is a typical complexity in dense urban traffic environments. Semantic graphs must support real-time reasoning under uncertainty, balancing computational efficiency with decision accuracy. These these stringent performance requirements drive the need for algorithmic optimization and approximation techniques. Hence, that was all about real-time performance requirements. And now let's discuss about algorithmic challenges and optimization strategies. Here we have three challenges. The scalability challenge, that is, large scale graphs with frequent updates present computational bottlenecks. Dense urban environments may contain thousands of nodes, or more than 1,000 nodes requiring continuous processing and real-time constraints. Stringent latency requirements demand highly effective algorithms. Decisions must be made within milliseconds to ensure passenger safety. And after that, an uncertainty handling. The uncertainty of this world, in that noise, sensor data, and unpredictable human behavior introduce ambiguity. Robust algorithms must tolerate imperfect imperfect information whilst maintaining safety margins. Here we have four important optimization strategies. Graph pruning to reduce search space, heuristic search algorithms like A pointer or IDA pointer, approximation algorithms for near optimal solutions, and parallel processing and GPU accelerations. Hence, that was all about algorithmic challenges and optimization techniques. And now finally, let's conclude the topic. Hence, semantic traffic scene graphs provide a powerful graph-based framework for modeling traffic environments in intelligent vehicle systems. Here we have to consider three aspects. Structured representation. Uh, the graph transforms raw sensor data into meaningful hierarchical knowledge suitable for algorithmic reasoning. And the algorithmic foundation. It leverages core DAA concepts like graph construction, traversal, shortest path algorithms, and optimization techniques, and real-world impact. It enables autonomous vehicles to interpret complex environments efficiently to execute safe, informed decisions in real time. As intelligent transportation systems continue to evolve, semantic graph representations will remain fundamental to achieve robust, scalable, and safe autonomous navigation in increasingly complex traffic scenarios. Hence, that was the conclusion. And finally, I would like to thank the respected professor to give me this wonderful opportunity to speak about this wonderful topic. Thank you.